Now that we've established all the things related to random variables, discrete and continuous, we will look into specific distributions that are special cases of the discrete and continuous. Go back to the diagram that I showed at the beginning of the random variables lesson. So a very specific example of discrete random variable is the binomial distribution. Now, all the specific examples below discrete will follow the properties of discrete, but each of these distributions have a particular pattern, which is why we gave them specific names and we investigate specific properties within those distributions. So an example of discrete that we're going to study is going to be the binomial distribution. So we're going to do all things related to binomial distribution. You can split this video into 2 lessons if you want to, but we're going to try and cover everything. So I want you to pause the video here and try and answer this question and see how far you can get to with it. Because understanding how this question works will help you understand how the binomial distribution behaves. So if I try to answer even starting with A, you will notice that the process becomes a bit tedious. If I want to see how am I gonna get 3 6s, exactly 3 6s? If I'm tossing 5 times, then I could get 3 6s and then no 6s, and then maybe no 6 and then 2 more here. Or maybe they show up at the end. Or maybe I have 2 combined here and then no number of 6s and then 1 and so on. And you can see it just becomes a bit long. And this should remind you of combinatorics a bit on how many ways the number of 6, how many ways a 6 can show up. So if I try and calculate the probability of this, and you've done something like this before, well, I need 3 6s to show up. So I need how many ways or in how many ways can they show up when I have 5 possible places for it to show up? How many y's can show up in there? That would just be like computing 5 choose 3. So let me choose the 3 spaces that they will show up, and these are how many ways it's going to show up. And that will be the number of different options that I will have in total. So once I compute that, then if I want to calculate the probability, I know that the probability is not going to change for each one because all of them, each one of these options will always have 3 of 7 over 10 showing up 3 times, no matter where you're keeping them. It's going to be 7 over 10 times 3 over 10 times 3 over 10 times 7 over 10 times 7 over 10. And I will always get this order, this number of 7s and 3s, just in a different order throughout. So it's always 3 lots of 7 over 10, and then I have 7 over 10 showing up 2 times. So this corresponds to getting exactly 3 6s. This corresponds to getting 2 no 6s. And then how many ways or how many options do I have for this? It's 5 choose 3. So have a close look at this again and try and see how the numbers relate and link it back to the actual name of the distribution. So hopefully this is a hint for you to notice that this is actually the binomial theorem in here, where you have n choose r, this will be n minus r, this will be r, and this is where the name comes from also. So when do I know that something is a binomial distribution? What are the properties? How do I get to use this formula in a more sophisticated way? This is what you need to know. So a binomial distribution has specific features. One of the features is that you always have a fixed number of trials, a fixed number of events that something is happening. It's not infinitely many. You are tossing a coin a number of times. You are attending school 7 days a week. So there's a specific number of trials that are happening. So in the starter, it was 5 because you're tossing 5 times. And then for each trial, for each toss, for example, you're thinking of 2 possible outcomes only. You either have a success or a failure, and what you decide as a success is based on the question. So for the starter, we have 5 trials, and for each trial, I will consider it a success if I obtain a 6, and the probability of that is 7 over 10. So my probability of success was 7 over 10. Now, an essential thing is that from trial to trial, that probability of success or the probability of failure do not change, which means all the trials are independent of each other. This is very important. So if you have things like, oh, I'm picking something out of a bag and not replacing it, it means that the subsequent events are dependent on the previous, which means it's not a binomial distribution. So it's only binomial if all the events are independent of each other. And you can see it doesn't matter if I throw the dice another time, the probability will still be a 7 over 10. So these are the essential features of a binomial distribution. Now, the question in the starter was based on a specimen paper. So I've just added an extra question in the beginning just to help us dive to binomial distribution a bit more smoothly. So since the parameters that define a unique binomial distribution are n, the number of trials, and p, the probability of success, so those two are what I need. Those are enough to help me compute all the things related to binomial distribution. This is the notation we use to define that something follows a binomial distribution. So we say x, the random variable x follows a binomial distribution with n number of trials and probability of success p. Okay, so that's how you define the binomial. And what is the formula? So you are sometimes expected to write out the formula. Sometimes if they're small numbers, you're expected to compute them in non-calculator papers, but that will be for small reasonable numbers. In order to show your work in paper 2, especially if you're using the calculator to show your work, you need to write out the formula. So this is how it goes. You have the n number of trials, and if you're looking for when is x equal to a specific number, so when am I getting exactly 3 tosses, this is where the 3 will go. This is the number of trials. And be careful that it's not exactly like the binomial theorem. You'll notice the binomial theorem is always written as n minus r and then r. In here, you want to make sure that your probability of success is equal to r, because this is how many times you want your event to happen. And then the probability of failure is always 1 minus p, because you don't have any other event happening. You're either a success or a failure. So the failure is always the complement of the success, and that will happen n minus r number of times. Alternatively, we sometimes define the probability of failure as q. So I define it as 1 minus p. And I can shorten the formula to n choose r, p to the power of r, q to the power of n minus r. We then have to be careful with things like at least or more than. Remember, you're dealing with discrete values. Discrete, this is very important. So if I'm looking at the probability of at least obtaining an x value, it is the same as taking 1 minus p, the probability of getting less than or equal to that value less. So for instance, if I'm doing 5 tosses and I'm looking for at least 3 x's, okay, it is the same thing as, remember, you're tossing 5 times. So I either get 0 sixes, 1 6, 2 sixes, 3 sixes, 4 sixes, or 5 sixes. If I'm looking for at least 3 sixes, it means I'm not looking for the 0, 1, and 2, which means I can take away x less than or equal to 2. So notice how this jump happens. I need to write it this way. This is why it says x minus 1. If I want more than an x value, so if I'm looking for strictly more than 3, it means I'm looking for exactly 4 and 5. So it's the same thing as probability of more than or equal to 4. Or it's the same thing as saying, okay, if I'm only looking at 4 and 5, it means I'm not looking at anything below 3 and below. So it's the same thing as 1 minus probability of less than or equal to 3. So you need to practice these equivalences to help you compute binomial distribution questions. We'll go for a demonstration. We'll go through how to use them on the GDC, how to compute them, but you also need to know how to write them in the formula itself. So the binomial is found in distribution. You can see it here. So second distribution. And you have to go all the way down and you'll see binomial PDF and binomial CDF. Now we use PDF when you have a question such as, I'm tossing a coin 100 times. What is the probability that the head will appear exactly 52 times? So I'm looking for exactly the probability being equal to something. So in this case, you use the PDF. So you're looking at x being exactly 52. In this question, x follows a binomial distribution of 100 trials, and then tossing heads and tails, the probability is always 1/2. So this is your distribution. The first question is asking, when is it exactly 52? As a formula, you need to write, well, 100, choose 52, 1/2 of 52, and then the failure is 1/2, and then you have 48 here. You can write this out, and then you can use the binomial PDF function. So PDF is used when you're trying to find exactly. So you would go PDF, we enter the number of trials, we enter our probability, we enter how many do I need? I need 52. And then I compute that, and it's going to give me the 0.735, 0.0735. So that's the 3 significant figures. So you can use the calculator, just make sure you also write the notation here. Now, when it's at most, so again, we have x follows a binomial distribution of 100 and 0.5. At most 52, it means the maximum I'm looking at is the 52. This is when things are cumulative. They're adding up. I'm adding up the number of trials for, I'm adding up how many times I'm going to get no heads and 1 head and 2 head and 3 heads, and it's just a lot of values to take. If you're dealing with an inequality, you're adding up you're adding up the probabilities. In this case, we use binomial CDF. So we go all the way down, you'll see binomial CDF. And you enter your number of trials, you enter your p-value, and you will enter what's the maximum you wanted to add up to. I wanted to get to, 52. I wanted at most to be 52. And you'll notice the number is different now for CDF because it's been adding up all the probabilities. It found the PDF for 0, the PDF for 1, the PDF for 2, and it started adding them up. Now, there's no notation for this. So there's no, because this formula, remember, is only for when it's equal to. We don't use any notation for this, but at least show this notation. And you can write this out, and the answer is 0.691. Now, what about at least? Okay, there will be at least 48 heads. So in here, if I'm looking for at least, so the least amount it can take is 48. So including 48. Now, the calculator cannot compute more than values. It's always computing less than. Okay, keep that in mind, which means you have to take into account if I have 100 trials and I want 48 and more, it's the same thing as saying 1 minus the 47 and less. So 1 minus the probability of getting less than or equal to 47. So when I go to the calculator, I have to type in 1 minus, go to the distribution. Again, we're doing cumulative, but this time 47, and you get your answer 0.691. Now, the fact that the answer is the same as at most is due to the symmetry nature of the distribution about its mean of 50. So it's just a coincidence for this one. But you need to make sure that you do the calculations correctly, do the 1 minus, write out the probability so that it's clear what you're doing. Now let's go back to the starter. Let's actually use the formula. So if I want the probability of getting 6 exactly 3 times, then I know I have n equals to 5, the probability of success 7/10, and I want r to be exactly 3. So using the formula, it's 5 choose 3, 7/10 to the power of 3, 1 minus 7/10, 5 minus 3. This will be the answer. And because I'm looking at equal to, I will use binomial PDF, enter all the values, it will give me the same answer. So you can compute this using combinatorics. You can also do it using binomial. This is the original question, so the exactly 3 6s was actually not part of the original question. I just added this in there. So this is the specimen paper. This is the actual question, how it was worded. It's a paper 2 question, so you're allowed a calculator. So the first question says at most 3 6s. So the maximum I could get is 3 6s. So it means I'm looking for less than or equal to 3, which means it's the probability of x equals to 0, x equals to 1, x equals to 2, x equals to 3. Now we can do a PDF for each one and then add them up, but that's a lot of work. We'll just do CDF and we will say that, okay, calculate up to 3 in there. So CDF up to 3, and it will give you 0.4178. Now, what if it says slightly differently? So the third 6 is on the 5th toss. So this means that the last toss is fixed. It's a y in there. So I know it's a fixed 7/10 here. So what happens with these 4? I have, do I have a bit of freedom? Well, no, it means that the previous 4 tosses should include 2 6s in there. So this time, how many trials do you have? Do you have 5 trials? No, you have 4 trials. And you're looking at when within those 4 trials will I get 2 6s? It means that you have now dived into a new binomial distribution. We will call it W because we need to use different letters, where I have 4 trials this time. And again, the probability of success is 7/10. And I'm looking for when is it within those 4 trials am I getting exactly 2 6s? So in that case, you calculate this normally. So going back here, you can calculate it normally. So binomial PDF, I have 4 trials now. The probability of success is 7/10. And I'm looking for when will I get 2 6s, and it will give me this. All right, so this is the probability of getting 2 6s. Multiply this by the fact that the 5th toss is fixed as a 7/10. So this will be 0.2646 times the fact that the last toss is 7/10, and that will give me 0.18522. Now, this practice of shifting the binomial to another new binomial is not new, so get used to this method here. All right, for all these questions, do pause the video, try them out on your own, and then have a look at my solution. So it will all depend on the fact that you've tried these questions so that it helps you understand them in an easier way. We will not do a probability distribution table for the week. You can if you want to, but it's just going to be too long. You're looking at 0, 1, 2, 3, 4, 5, 6, 7. So basically, you're looking at how many times will the package never arrive on time, arrive once on time, twice on time, 3. So basically, binomial PDF where x is equal to, sorry, r is equal to 0, r equal to 1, r equals to 2, and so on. So we're not going to do that. We're just going to answer the question directly. So it says, find the probability that on the 7 days they deliver the package before 9 a.m. on 5 occasions. So this, it's better to always define it. You have 7 trials going on, and the probability of success is 0.7, because my focus is that it delivers by 9 a.m. So if it doesn't deliver at 9 a.m., that the probability is 0.3. So if I want the probability that it delivers exactly 5 times, then it's 7 choose 5, and I want this success to happen 5 times, and the failure to happen 7 minus 5 times, which is 2 times. So on the binomial PDF, you will have 7, you'll have a probability of success, and you want it to happen exactly 5 times. So it's going to give you 0.317. Just going to write it here, 318. Now, find the probability that he delivers the package before 9 a.m. at least 5 times during the week. So I need at least 5 times. You can either directly do it as, okay, if it's 5 out of the 7, or at least 5 out of the 7, it means it's the probability equals to 5, equals to 6, equals to 7. So we can do PDF of each one directly. I also know that it's the same as 1 minus the probability that it's less than or equal to 4. So remember, on the 7 days, because we're dealing with discrete values, so there's 5, 6, and 7. If I want to know at least 5 times, it means I need to do 1 minus the 4 times. And don't forget 0. So I can go and say, well, it's 1 minus 1 minus the probability, this time CDF. I have 7 trials, 0.7 as a success, and I wanted to calculate up to and including 4. So 6. I've already done the subtraction. Just make sure that you do the subtraction also. And it's going to be 0.647. Okay, or you can do individually 5, 6, and 7 and add them up. You can do that if you have time, just to double check that your answer is the same. All right, this is an interesting question. Something else is missing in this question. So again, I would encourage you to pause and try this out. So in this case, we don't know the number of trials. Hopefully you've noticed that. We don't know how many trials there are. So X follows a binomial distribution. I don't know the number of trials. I know the probability of getting a red is going to be 3/8. So that's my probability of success. But it's asking me how many trials do I need to do such that the probability of getting at least 1 red is bigger than 0.9. So always translate the information into some notation so that helps you understand how to compute these values. X bigger than or equal to 1 is the same thing as 1 minus probability of X less than or equal to 0. And obviously I can't go less than 0, so it's the same thing as X being equal to 0. All right, and then I can compute X being equal to 0 by actually using the formula, or let me rearrange these values. So I get 1 minus 0.9, which is 0.1, and probability of X being equal to 0. Well, I'm stuck here. I don't know anything about N, but I know the formula that it should, that it would apply to. So it's N choose 0 of 3/8 0 to 5/8 n. N choose 0 is just 1. 3/8 to the power of 0 is just 1. So I'm left with 5/8 n. You can use the GDC up to this point, or we can use logarithm. So log 0.1, sorry, oops, and then log of 5/8. Being careful that log 5/8 is a negative number, which means when I divide it on the other side, the inequality is going to switch. and I end up with 4.899 n. So n has to be bigger than 4.899 as the number of trials, so it has to be an integer, which means the smallest possible value that it could take would be 5. And you can check your answer, substitute in. If I go to the distribution and I go, which is 1 minus, so 1 minus the probability of getting, if I have 5 trials, probability is 3/8 and 0 here. It is bigger than 0.9. So this is an example where one of the parameters is missing. So n was missing here. We'll see an example at the end where p is missing. Now, what about expected value and variance? The expected value is easy to find. It's just, remember before, it was always the number of trials times the probability. We've done this when we did probability as a lesson, and the same rule applies here. So the expected value of a binomial distribution is just n times p. The variance is also easy to compute. It's just n times the number of success times the number of failure, or n times p times 1 minus p. So it's very easy to compute. If you square root this, you get the standard deviation. Practice this question. Typically shows up. They give you the expected value of the variance, and you need to find the number of trials and success. So have a go at this one. And this would be the solution. So we're just using the formulas, equating where we need to, and then rearranging and solving, keeping in mind that q is not a new variable. Q is just 1 minus p in here. So, all right, not the last, but you can pause and practice this question also. And then you can have a look at the solutions. I'm going to directly just write out the solutions for these, but let's just write out the distribution. Follows a distribution of 5 trials and the probability of success being 0.4. So for part A, we need x to be equal to 3, and that will be 5 choose 3, 0.4. 0.62, so you write it out and then use binomial PDF, and it should give you 0.2304. For B, at least 3 days, so bigger than or equal to 3, which is 1 minus the probability of x being less than or equal to 2. And just as a final answer, that's going to be 0.317. That's the 3 significant figures. Now on C, there are different ways to think about C. I'd rather think of it as more of a combinatorics method. If the 3 days have to be consecutive, so 1, 2, 3, 4, 5, if they have to be consecutive, first of all, we know that's going to be 0.4 to the power of 3, and then we have the 0.6 to the power of 2. So that will always be fixed. But the 3 that are consecutive, how many places can they go? So imagine them as a full block. If they are a full block, then I can only, so you can imagine there's 1 place, 2 places, and 3 places they could go in only. Or another more sophisticated way to think about it is that because they're taking up 3 spaces, so imagine you now have, this is 1 space, and then you have 2 more spaces to pick from. So this 0.4, there's a 3 choose 1 number of ways that you can place them in. So out of all these probabilities, there are 3 choose 1 ways to arrange them, or there are 3 places to choose from, because 3 choose 1 is just 3. So in this case, you get 0.6912. And then the expected value, quite easy. We just multiply the 5 with 0.4, which means we get 2, which means as we repeat the experiment, a lot of time we are expected to get 2 days on average. And then the variance or the standard deviation, will be the square root of 0.4 times 0.6 times 5, which is going to be 0.219. Sorry, it's going to be 1.10. That's the 3 significant figures. So practice these questions. These are SL type questions. These are the answers. And then you have the HL specific questions with these as the answers. And then you have like an exam style question that you can go through. And I just want to discuss one more example of missing parameters. So in this case, you can pause and try part A on your own. I'm going to focus on part B. Part B, the probability is missing this time. So how do we approach it? So you have 10 people, and it says that the probability of exactly 6 people buying or wearing the glasses, so 6, that 1 minus p to the power of 4 is 0.219. So how do we find the possible values of p? In this case, you're allowed a calculator. So how do you compute it? Well, you actually write this in y1 and y2, find the intersection, but you need to adjust the window. So every time things are missing in binomial theorem, or binomial distribution, sorry, rely on the formula for the binomial distribution to help you solve these questions. So if I graph this, you'll notice there are 2 points of intersection. The question should have said find 2 possible answers, and that would be 0.678 or 0.518. In reality, there are 4 possible answers. I can rearrange this. I can move this to the other side and make it negative so that it's equal to 0, and then I'll be finding the intersection, the zeros with the x-axis. So there are 4 solutions, but 2 of those are not possible. You cannot get a probability bigger than 1 or a negative probability. That's why it's only 2 options. Again, there are more questions with missing parameters that you can practice on with the answers, and then make sure you familiarize yourself with the summary here.